Hello friends, today we solve the semiconductor physics problem of GATE 2023 electronics and communication paper. So this is the first question. It is saying that in a semiconductor, if the Fermi energy level lies in the conduction band, then the semiconductor is known as degenerate N type, degenerate P type, non-degenerate N type, non-degenerate P type. So if the Fermi energy level of the semiconductor is lying in the conduction band, then we call such semiconductor as degenerate N type. So the dictionary meaning of the word degenerate means to become worse or lower in quality or characterless. Okay, so when something loses its original character, then we call it degenerate. Okay, so degenerate semiconductor are those semiconductors which act more like metals and less like semiconductor due to very high concentration of dopant atoms. Okay, so you know that higher the n type doping in a semiconductor, then closer will be the ef to ec level. So in degenerate case, what happens is they act more like metal because of the very high doping of around like 10 raised to power 19 to 10 raised to power 20 dopant atoms per centimeter cube. So due to such high level of doping, the Fermi level goes in the conduction band, okay, and they act more like metal. So we call such semiconductors as degenerate N type. So if the EF lies in the valence band, we will call it degenerate P type. Non-degenerate N type means EF is closer to EC, but there is some distance between them. Okay, so normally we only study these in our syllabus. These are more of a metal and less of semiconductor, so we do not study their properties much. Okay, so this was theoretical question. Second question is again theoretical easy question. For an intrinsic semiconductor at temperature T equal to 0 Kelvin, which of the following statement is true? So all energy state in the valence band are filled with electron, and all energy state in the conduction band are empty of electrons. So this is true. All energy state in valence band are empty and all energy state in conduction band are filled with electrons. False. All energy state in the valence band and conduction band are filled with holes. This is false. All energy state in valence band and conduction are filled with electron. This is also false. So at absolute zero or at T equal to 0 Kelvin, uh, in terms of band theory, no electron in the valence band has thermal energy to go to conduction band. So all the electrons lies in the valence band and no electron can jump to conduction band because there is no thermal energy. Okay, so all energy state in the valence band are filled with electron and all energy state in the conduction band are empty of electrons. Or in terms of bond theory or chemical bond model, no energy is there to break any covalent bond between silicon atoms in the Si crystal. So no free electron is there to move freely inside the crystal, hence it acts as a insulator. Okay, so he is correct. All the electrons are only in the valence band and no electron can go into the conduction band. So A is correct. All energy state in valence band are filled with electron. All energy state in conduction band are empty of electron. Okay. Third is again theoretical question on MOSFET. For a MOS capacitor, VFB and VT are the flat band voltage and threshold voltage respectively. The variation of depletion width for a varying gate voltage VG is best represented by. So here you can see that four graphs are given where they vary VG and they want to know the variation of W depth. So you can see that in all four VT is positive, so threshold voltage is positive, means it's a N channel MOS capacitor, which means it has a P type substrate. So let's try to understand qualitatively how depletion width varies uh, as we vary gate voltage. Okay, so first let's try to understand what is accumulation mode. So accumulation, depletion and inversion, all three terms are with respect to majority carriers. Okay, so for n channel MOSFET the substrate is p type. Okay, so in accumulation mode, as the term says, there is an accumulation of majority carriers near the surface. Okay, so how do you, so in say p-type substrate, so how do you accumulate majority carriers? Or will obviously we will apply some negative charge here, so that the holes, the majority carriers can accumulate near the surface. Okay, and electric field will be in this direction, because this side is negative, this side is positive, so electric field will be like this. Whereas if it would be a p MOSFET, okay, then what would happen to accumulate majority carriers, which means for n substrate we need to accumulate electron here, so here you will apply slightly positive voltage on the gate. Okay, and electric field will be like this. So accumulation means accumulation of majority carriers near the surface, so you need to apply Vg equal to negative. As you can see here, in all four, for the accumulation the voltage is negative. Okay, now depletion mode means depletion of majority carriers near the surface. So how do you do that? By repelling majority carriers away from the surface. So to do that, what will we do? We'll apply small positive charge. Okay, so that the holes can be repelled away from the surface, and what will happen is depletion region starts to form near the surface and continues to increase as Vg increases. Because once the holes are pushed back, then the negatively charged acceptors are exposed. So when the holes are pushed, the negatively charged acceptors are exposed. Due to this positive charge, holes are repelled, so negatively charged acceptors are exposed, and some electrons, then minority carrier, will also be attracted toward the surface. So slowly inversion will also begin, and depletion layer will start to form in this type. If it would be p channel MOSFET, then to deplete the surface of electron we need to apply a small negative charge, so that electron can be repelled and holes starts to accumulate. Okay, electric field will be like this. Now in strong inversion, what will happen is accumulation of minority carrier near the surface happens. So inversion means as much minority carriers near the surface as there were initially majority carriers near the surface. So to do that, what will we do? We'll apply large positive charge. Okay, so that lot of electrons can be attracted near the surface and lot of holes can be repelled. So in strong inversion, what will happen is n channel will form near the surface, and depletion width will start to from depletion mode, and then it will continue to increase till a voltage called threshold voltage. So depletion width will increase till VTH. Okay, so W depth almost become constant after when VGB, so between gate and body, increases and reaches VTH. Okay, because after that the surface potential become fixed. So this is the case. So in case of n minus substrate case, so suppose it's a p channel MOSFET, then we will apply large negative voltage here to attract minority carrier, that is holes. Okay, to attract all the holes near the surface, and VTH is negative for a MOSFET with n type substrate, and p channel is formed near the surface. So here also depletion width will be formed of positive of these positive ions. Okay, here there will be negatively exposed ions. So VTH is applied VGB, at which we have onset of a strong inversion and a proper n channel is formed. So after VTH, W depth get maximum at VTH and then remain constant. Okay, so you can see accumulation, and then there is depletion, then there is strong inversion. So between accumulation and depletion there is flat band, in between depletion and strong inversion there is VTH. Similarly for p channel MOS capacitor, first there is strong inversion, then depletion, then accumulation. Why? Because here for large negative voltage we have strong inversion. Okay, so this way it goes. So this was the qualitative idea that W depth is 0, depletion width is 0, because there is no minority carriers or no expose of majority ions. Okay, so no, so from depletion width slowly the depletion region depletion width start to form. Okay, and then it continue to increase till VTH is introduced. Okay, till we increase VG to VTH. So based on this you can see that two graphs are there for which in accumulation mode depletion width is 0 and then after VTH it become constant, but here you can see that it is reaching maximum value at 0 voltage only, whereas in this case it is reaching maximum value at VTH. So this is correct answer for this question. Okay. If you want to talk in terms of formula, then you can see that for Vg less than VFB flat band voltage accumulation mode is there, so WDAP is 0, and for Vg between VFB and VT depletion mode is there and slowly weak inversion also starts, so WDAP keep on increasing. Okay, and the formula is like this: WDAP is equal to under root 2 ESI and then psi s by QNA. This is the doping concentration of the substrate and this is the voltage drop across the semiconductor surface or substrate potential. Now as Vg increases, psi s increases and WDAP is inversely proportional to psi s, so which is like also inversely proportional to Vg also. Okay, so as we increase gate voltage, surface potential psi s also increase, so WDAP also increase. So this is the correct answer. This is the correct answer. So it will keep on increasing till VTH. After that depletion width does not increase. So B is the correct answer. Another question is on in an extrinsic semiconductor, hole concentration is given by 1.5 Ni, where Ni is the intrinsic carrier concentration of 10 raised to power 10 per centimeter ratio of electron to hole mobility for equal hole and electron drift current is given by. So electron and hole drift current needs to be equated and we are given a hole concentration in terms of Ni. So you can see that drift current due to electron is N Q mu E and drift current due to hole is P Q mu P E. Okay, this is current density, so current which is current per unit cross sectional area, so current drift current due to electron will be N Q mu E and then this is simply I by A, so A will go this side and simply I drift due to hole, H means hole, P Q mu P E A. Okay, now we need to equate both of them, so I will simply equate them. So now A will cancel because same cross sectional area, because same semiconductor, electric field will be same, Q electronic charge will be same, so basically it is N times mu is equal to P times mu P, so we need to find mu E by mu P, so which is P by N. So the whole concentration is 1.5 into 10 raised to power 10. Okay, it is given whole concentration is 1.5 Ni and Ni is given, so 1.5 into 10 raised to power 10. And now electron concentration we can found using mass action law, that Np is equal to Ni square, so N is equal to Ni square by P. Now Ni square is Ni is 10 raised to power 10, so Ni square is 10 raised to power 20 divided by P, which is 1.5 into 10 raised to power 10. So this is basically 10 raised to power 10 into 1 upon 1.5. So when I put it and I get them, so this is 1.5 by 1 into 1.5 by 1, so this is 2.25. So this is the ratio. So we just need to simply equate these two. Drift current due to electron is NQ mu Ne and drift current due to hole is PQ mu P E. This is mobility, this is electric field, and this is electron concentration, this is hole concentration. Okay, so again simple question. Last question is on again basics of semiconductor. In a semiconductor device, the Fermi energy is 0.35 electron above the valence band energy level. Effective density of state in valence band at T is equal to 300 Kelvin is 10 raised to power 19 per centimeter cube. The thermal equilibrium hole concentration is silicon at 400 Kelvin is. So here there is one problem in this question, that he has not specified this Fermi level is above valence band by 0.35 electron volt at 300 Kelvin or 400 Kelvin. But since we need to find it at 400 Kelvin, so we'll assume it at 400 Kelvin. Okay. So we can either assume it as constant or we can assume it at 400 Kelvin. So to find whole concentration at 400 Kelvin, which is say temperature T2, I need NV2 e raised to power minus EF minus EV by KT at temperature 2. Okay, because he has also specified value of KT at T is equal to 300 Kelvin at 0.026 electron volt. Okay, so I need NV2, I need KT2, EF minus EV. I am assuming that this thing is either constant or it is at or it is given at 0.35 electron volt. Okay, so this is more correct because EF will vary as temperature will increase. So I will assume that this data, so this data is given known. Now to find KT2, I will use that KT is proportional to temperature. Okay, so KT2 by KT1 is equal to T2 by T1. So KT2 is nothing but T2 is 400 Kelvin, T1 is 300 Kelvin, so 4 by 3 into KT1. KT1 means value at 300 Kelvin, which is given to be 0.026 electron volt into 4 by 3, so this is 0.0346 electron volt or 0.035 electron volt. Okay, so KT2 is also known, this part is also known. Now how to find NV2? So for NV1 and KT1 are given, so since NV is 2 into 2 pi mp star KT by h square raised to power 3 by 2, so this means NV is proportional to T raised to power 3 by 2. So NV2 by NV1 is T2 by T1 raised to power 3 by 2, which is basically 400 Kelvin by 300 Kelvin. So this is 4 by 3 raised to power 3 by 2. Okay, and NV1 is given to be 10 raised to power 19. Okay, effective density of state at 300 Kelvin is 10 raised to power 19. So this part is given and this is known. So basically it is 4 by 3 under root 4 by under root 3 raised to power 3. So this is 2 by root 3 cube. So this is 8 by 3 root 3. So I solve it. So 1.539. So this is basically 1.54. This is into 10 raised to power 19. Okay, so this term is also known. So this is 1.54 into 10 raised to power 19, and this part is given to be 0.35 electron volt. This was found to be 0.035 electron volt. Okay, so this is basically 1.54 into 10 raised to power 19, and then this is nothing but e raised to power minus 10. So when it will come down, so it will 1 upon e raised to power 10, and this is 100. So this thing becomes equal to, when I solve it, simple calculation, then it becomes 69.916 into 10 raised to power 13 per centimeter cube. Actual value of table answer was between like 61 to 70. Okay, so this is valid, also good. So the correct answer is 69.916. Okay, so these were all the 5 questions. Thank you.